Here I'm going to show you sort of a shortcut that often works when you're doing integration by parts. It doesn't always work, so I'm including an example that for which it wouldn't work. But we've looked at integration by parts. Let's apply it here first, then I'll show you the trick that you'll probably end up using most of the time. So here I'd probably let my u be x, my dv be sine of x dx, and therefore du is 1 dx, and v is the antiderivative of sine, which is negative cosine. So integration by parts would say that this integral is equal to uv, which would be negative x cosine of x, minus the integral of v du. These can both turn into a plus if you bring that out. So then I get negative x cosine of x, and the antiderivative of cosine is sine. So that was pretty easy. However, there's another one that would be, or another technique called tabular integration, which would make a problem like this much easier. And maybe even not in particular this one, but if this was like x to the 3, then we would want to use tabular integration, which I'm about to show you. So here's how tabular integration works. And all it is a shortcut to integration by parts. So the way it works is you make a table. The left column you call your u, and the right column your dv. So the assignments are still the same. We let our u be x and our dv be sine of x. You don't really need the differential in this table. So now what you do is you take the derivative until you get to 0. So the derivative of x is 1, the derivative of 1 is 0, and now we're done. And then you take the antiderivative of the right column until you match up to the 0. So the antiderivative of sine of x is negative cosine of x. The antiderivative of negative cosine of x is negative sine of x. And then what you do is you draw these diagonals, and you take the positive product, and then you add that to the negative product here, and you would continue in that fashion if you had more rows. The positive product plus the negative product plus the positive product. So the positive product would be x times negative cosine of x. So that's this. And I'm going to add that to the negative product of 1 times negative sine of x. So 1 times negative sine of x is negative sine of x, but the opposite of that product is a plus. So there it is. So that technique comes in really handy if you had something like this. Let's say you had to do this problem, x, to the 4th sine of x dx. Then you let your u be x to the 4th, take derivatives till you can't take them anymore. Take them correctly, of course. 24x, 24, 0. And then put a sine of x here and take antiderivatives till you can't anymore. So that would be negative cosine of x. And then the antiderivative of negative cosine is negative sine. The antiderivative of negative sine would be cosine. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine. And now I take the positive product plus the negative product, positive product, negative product, positive product, to get that my final answer is negative x to the 4th cosine of x plus 4x cubed sine of x plus 12x squared cosine of x minus 24x sine of x minus 24 cosine of x plus c. You can see why, so that's the answer to that one. Sorry to squeeze that in like that. But you can totally see how useful this tabular integration can be if you're in a situation where you notice you would have to do integration by parts like 5 times. It's not feasible, so definitely use this technique when you can. It works well usually when you have a polynomial times a cyclic derivative. So like, x to the fourth is a polynomial, and sine of x has a cyclic derivative, cosine does as well, e to the x or anything, e to the 2x, those type of things. This is a perfect situation in which you'd want to do that. Again, it doesn't always work. I'll give you an example where it wouldn't work, but often it does, so you might want to use this as much as you can. Here we're going to look at another tabular integration problem. It shouldn't take long because this is a quick technique. So I'm going to use integration by parts, or start it as though I'm using integration by parts. And what you do is you make your table, and let's let our u be x and our dv be e to the 2x. Again, you can leave out that differential for this problem. The derivative of x is 1, the derivative of 1 is 0. The antiderivative of e to the 2x is e to the 2x times a half. Be careful because you have to undo the chain rule. And then the antiderivative of that would be e to the 2x times a fourth. And so now we take the positive product and we're going to add it to the negative product. So our final answer would be 1/2 x e to the 2x minus 1/4 e to the 2x plus c. Here's a situation where you can't use integration by parts. So we've already done this problem. Even if you tried, let's say you broke this up and said, okay, I'm going to let my u be what you let it be last time, ln of x, and my dv be 1. Well, then what happens is when you take the derivative of ln of x, you get 1 over x. You take the derivative of that, you get negative 1 over x squared. We're never going to get to 0. So, yeah, I mean, not only that, we've got the derivative of 1, or sorry, that's wrong. The antiderivative of 1 is x. And then the antiderivative of x is 1/2 x squared. But the point is, if you follow this technique blindly, you really don't ever stop this process here. So, I mean, I'm sure there's a way you can kind of fudge with this table and kind of make it work out as though you did integration by parts, but as a rule of thumb, don't just think you can do every integration by parts problem using tabular. Sometimes you really just need to do it out the long way. So I'll finish with one more example of tabular. This is a problem I said I'd revisit. So if I let u be my x squared, because that will differentiate to 0, and my dv be e to the x. And this is awesome because the antiderivative of e to the x is just e to the x. So I'll take the positive, the negative, and the positive products. So it's x squared e to the x plus 2x e to the x plus 2 e to the x plus c. And that took us less than a minute. If you go see how long it took us when we did it the long way, you'll notice how appealing integration by tabular integration can be as a shortcut to integration by parts.